everybody. Hope you're fine. Had a nice holiday. Again, I have problems with my internet connection because my Swiss data, I had 100 gigs of data roaming. It's over. I bought 200 gigs from a French operator, but they did something very stupid. They told me it would work in my router, and it doesn't work in my router, so I had to order a new SIM card with their router, and it's going to arrive, I guess, tomorrow. So for today I'm still blocked. Okay, according to my records, we were on page 38 practicing this geometrical optics, and I'm going to try to finish this today. We have a few exercises to do. I gave you on page 38, I gave you 11 and 12 to second 11 because there is a problem with numbering. I'm very sorry about that. Okay, so we start with this exercise 11. A luminous object AB is located 250 millimeters from the optical center of a convergent lens of focal distance 150. How far from the optical center is the image? Okay, let's do it. Let's choose a scale. What if I can do divided by 5. If I divide by 5, it's not bad. Okay, so let's divide this by 5. So this 250 millimeters will become 50 millimeters. Okay, this will become 50 millimeters, and this divided by 5 will give us 30 millimeters of focal distance. Okay, let's now draw the optical axis as usual. Let's put a lens somewhere. It's a convergent lens, so we put the arrows this way. Okay, and then the object is 50 millimeters according to our scale, 50 millimeters away from the optical center. The object is here. They don't give a distance, so I will do 5 squares high. And we want a convergent lens of focal now 30 millimeters, so I'm going to put the focal points here. This is the image focal point, this is the object focal point. Okay, we want to know how far the image will be, so let's do it. You know how to do that, we did it many times. This is an easy exercise. You just need to draw the principal rays. Note that the height of my object doesn't change anything. Okay, if I have this object, I will have an image with a certain size. If I have a higher object, I will have an image which is higher, but the distance from the lens where the image is going to be will be just the same. Okay, so let's draw our principal rays. Here we have one, the one that arrives parallel to the optical axis, and this guy is continuing and passing through the foyer, through the focal point, sorry. And here we have one ray which is passing through the optical center, which is going straight away. Okay, so now we have here the intersection, and so the image is here. Okay, what is the distance from the image to the lens? It's 66 millimeters, and so therefore if I multiply by 5, I'm lazy to do it by head, 66 times 5 is 300 30 millimeters. Okay, so the answer to that question is P prime. This is the distance between the lens and the image. P prime is 330 millimeters. Of course, you give the answer in the original dimension. It's not in the reduced dimensions. Okay. Question B, is the image A prime, B prime real or virtual? It's of course real, because you have a convergent lens. You are not between the focal point and the lens, and furthermore, you see it very well here. You have light rays arriving. You can illuminate this image. It's a real image. You can project it on the screen. Okay. Good. Now we have a diverging lens. Notice that for a diverging lens, we have a negative focal length, which is normal. Okay. And we have an object which is 150 millimeters from the lens, and we want to find an image. Of course, what do you think? It's going to be real or virtual? It's going, of course, to be virtual, okay, because this is a divergent lens. Okay, so let's try with the same scale. Let's divide by maybe by 5. It's well, okay, let's divide by 5. So this 150, so the scale is 1/5. Okay, so these 150 millimeters, they become 30 millimeters. These minus 100 millimeters, they become minus 20 millimeters. And now we draw our system. We have our optical axis. I will put the lens here. It's a divergent lens. Don't forget to do the symbol properly. And then we have an object which is 30 millimeters from the lens. So it's here. The height of the object is not specified, so let's take 5 of these little squares. Okay, the object is here. This is point A, this is point B. Now we have a focal length of 20 millimeters, so 2 centimeters. So the focal points are here and here. Okay, and now let's construct the image. So you remember how we do that? We construct the principal rays, but we use this focal point to decide about where they are going. So here we have one ray which is arriving parallel to the optical axis, and this ray is going to leave in the direction given by the focal point. It's going to leave this way, and then we have the other ray passing through the optical center and going straight, and so we have an intersection here, and our image, so the image A prime, B prime, it is down here. Okay, and now if you want to answer at what distance we are, I have here 12 millimeters, so we have P prime 12 millimeters. If I multiply it by 5 to go back to the original dimensions, it's 60 millimeters. Okay, so the answer to question A is now 60 millimeters. Answer to question B, it's a virtual image, of course. The light which is leaving here doesn't arrive on the image. Okay. Okay, these were the two exercises you were supposed to do for today. Now we are going to continue. So please, every time we do an exercise, stop the video, do the exercise, and then watch the correction. Do it, come back. Okay, what do we have here? We have a convergent lens. Let's be a bit more formal for this one. Okay, we have a convergent lens. The height of the image is 48 millimeters. The height of the image is what we called G prime in the notation I use. Okay. The distance from the object to the optical center is 1.2 meters. Distance from the object to the optical center, this is what is called P. P is 1.2 meters. Okay, so it's 1200 millimeters. Okay, and that of the optical center, the distance between the object and the optical center, and that of the optical center to the screen is 36 centimeters. So optical center to the screen, this is P prime because the image forms on the screen. Okay, and so this is the distance between the lens and the screen, lens and the image. So P prime, we said, is 36 centimeters, which I'm going to write in millimeters, 360. Good. Now we have to decide about a scale. So here we could do 1/10. Okay. This will be, if I do 1/10, this will be 120 millimeters or 12 centimeters. So let's assume that this gives us 12 centimeters. This I divide by 10, so it's going to be 0.48 centimeters, okay, 4.8 millimeters. And here, if I divide by 10, it's going to become 36 millimeters, so 3.6 centimeters, right? And I'm going to start pretty far on the left with my object. Okay, let's draw the optical axis. Optical axis. Let's put our object somewhere, let's say here. Okay, and we don't know the height of this object. Okay, that's fine. We don't know the height. Okay, and now we have 12 centimeters from that point. So 12 centimeters, I have to use this ruler. 12 centimeters, it's here. So here we have our convergent lens, and the distance from the object AB is 1.2 meters, that's okay, and that of the optical center to the screen is 36 centimeters. We said 3.6. It arrives here. Okay, so let me extend a bit. Okay, so here we have our screen, and on the screen we know that the image has a height of 0.48 centimeters. Okay, it's not going to be very precise, but let's do it. 0.48 arrives here. Okay, at this height here, the height here is G prime. Now, how can I determine the height of the object? I'll let you think a bit. It's actually quite simple. We know that there is one of the rays which is not deviated, and it passes through the optical center. Okay, so this ray here determines the height of the object here. Okay, this is AB, and it determines a height which is called G, the height of the object, and this height is how much? Here I have, oh god, I don't see, I'm sorry, I have 17 millimeters, and and 17 millimeters, if I multiply by 10, it's 17 centimeters, which sounds okay. So the answer is, if the image has a height of 3.6 centimeter, the object has a height of 17 centimeters. You can even now determine the focal length of the focal distance of the lens, because you can take the ray which is coming out parallel to the optical axis, and this ray has to go here and to intersect the other one, and so this here determines the focal point f prime, and so we can put this on the other side. It's 27 millimeters, 27 millimeters. This is f. Okay, good. Sorry for moving the page. Now look at this and let's check a bit now, because the precision we have is not good. Let's check a bit the law of lenses. Okay, we have P, which is, I take now the original dimensions, P, which is, I will put it in centimeters now, I'm tired of this millimeters. We have P, which is 120 centimeters. We have P prime, which is 3.6 centimeters. We have F, which is, how much did we say? 27 millimeters. I said 27 millimeters times 10, it's 27 centimeters. And what else? We have here G prime, which is 3.6. Sorry. We have G prime, which is 4.8 centimeters, G prime, and we have G, which is 17 centimeters. So let's check. First of all, let's check the law of lenses. Do we have 1 over f equal to 1 over p plus 1 over p prime? How do we know that? Well, we just compute. Okay, here just use the same unit everywhere. Here f is 27 centimeters, so it's 1 over 27, and here it's 1 over p, which is 1 over 120, plus 1 over p prime, and p prime is 36. Okay, let's see. It sounds okay, but let's check it. 1 over 27 is 0.037 approximately, and here 1 over 120 plus 1 over 36, this gives us 0.036, and then there is ones. Okay, so you see we have a good agreement between the left side of the law of lenses and the right side, and this agreement we check it numerically, and in a case like this, this is of course much more precise if you want to compute the various dimensions than doing the drawing, because in this drawing, due to the large distance, the small side of the image, you have a lot of distortion, a lot of errors. Okay, now let's check the second law. P prime over P is G prime over G. What is P prime over P? P prime is 36 centimeters over P, which is 120 centimeters, and on the other side G prime is 4.8 centimeters and G is 17 centimeters. Again, it looks okay, but let's check. 36 divided by 120, this is 0.3. Okay, and 4.8 divided by 17, this is 0.282 approximately. Okay, so again we have an acceptable agreement numerically between the two sides of the law of magnification this time, right? Okay, let's go to the next one. Please do it and then come back. So let's read what all this is saying. We place a luminous object of height 6 millimeters. So let's identify properly the things here. The height of the object is G, and G is 6 millimeters. This object is at 50 millimeters from the optical center, so this is P, and P is 50 millimeters, of a diverging length of focal minus 75 millimeters. Okay, so this is wonderful because we can use just the original dimensions. I guess we don't need to scale that down. We don't need to scale that down, and so now I can draw my optical axis. Okay, on that optical axis I can put some object which is 6 millimeters high. So let's take the object to be here, and 6 millimeters, that's 3 of these small squares on my drawing. Then we have 50 millimeters from this object, therefore here. Well, actually, I'm very sorry. I realized that exercises 15 and 16 have not been translated. I'm sorry. This is something I missed when I translated the course for you guys. Okay, so I don't have time to translate it now. Let's do it in French. Voila. A luminous object AB of 12 centimeters height. So this is G. Okay, it's a luminous object. It's an object producing light. It's at 32 centimeters of the optical center of a convergent lens of focal 20 centimeters. Okay, and so you want to know where the image is. So this is quite basic. What should we do? Let's divide by 5 maybe. Okay, if we divide by 5, 12 divided by 5, this is going to give us 2.4. 32 divided by 5, it's going to be 6.4. 32 divided by 5, yes, it's 6.4 centimeters. And focal divided by 5 is going to be 4 centimeters. Okay, let's draw this system. Optical axis, we have some object of height 2.4 centimeters. Okay, it's a big object, but doesn't mean anything, big object. Okay, here we have our object of height 2.4 centimeters, and we know it's at 6.4 centimeters, 6.4 centimeters of the optical center of a converging lens. Okay, and this converging lens has a focal of 4 centimeters in reduced dimensions, so it's here and here. This is f and this is f prime. Okay, once you have read the problem statement properly, a good part of the job is done. Okay, now we need to construct the image, so you know how to do that. Okay, you take a parallel to the optical axis. If it arrives at the end of your drawing, don't worry, you could have drawn it longer. Okay, and so the ray which arrives parallel to the optical axis will go down through the foyer to the focal point, and now we have a second ray which is going to arrive like this, so it's not long enough. Let me take another one. Okay, and so now I have my other ray which is arriving here, and so this one I should extend it a bit, and we have an intersection here, so we have an image which is here perpendicular to the optical axis, which I can extend if you want. Okay, good. So we had here the distance P, which was reduced 6.4 centimeters, and so now we can identify P prime, and P prime is the distance between the optical center and the image, and P prime is 10.4 centimeters. Okay, and the height of the object was 2.4 centimeters, and the height of the image, we can measure it now, it's 3.8. Okay, so here G prime is 3.8 centimeters. Okay, let's check the laws of lenses. So the answer to question A, where should we place the screen? Of course, the screen should be placed here at the place where the image is formed. Okay, so this is P prime is equal to 10.4 times 5. This is 52 centimeters. Okay, and the height of the image, it's 3.8, but we need to multiply by 5, so 3.8 times 5 is 19, so G prime is equal to 19 centimeters. Oh God. Oh God. We have here the problem in French and then in English. Okay. Okay. So we did it. So we did it, and we even have the English version. I'm so happy. Good. Now, one thing I would like to do with you, of course, is to check the laws of lenses. So let's do it on a different page. Let's first write down all our dimensions, and let's write down the original dimensions, not the reduced ones. Okay? Because I prefer to work with the original dimensions. So P is 32 centimeters. P prime is, we just computed it, 52 centimeters. G is 12 centimeters. G prime is 19 centimeters. Okay, and the focal distance is 20 centimeters. Now let's check the laws of lenses. We don't need the drawing any longer. Let's check the laws of lenses. We have 1 over f is equal to 1 over p plus 1 over p prime. And so 1 over f, it's 1 over 20, and the other side we have 1 over p, which is 1 over 32, plus 1 over 52. It sounds okay. 1 over 20 is 0.05, as everybody knows. And here we have 1 over 32 plus 1 over 52, and this gives 0.0504. Okay, so we have a good agreement between this side and this side. Numerically, we are very happy. This was for the law of lenses, and now the magnification law. G prime over G is P prime over P. Okay, P prime over P is 52 over 32, and G prime over G is 19 over 12. Sounds good. Sounds good. 52 over 32 is 1.625, and 19 over 12 is 1.583 periodic. So we are quite happy. 158.3, 162.5. It's okay. Okay, this is quite typically how the laws of lenses perform once you analyze a drawing that you have done by hand. Very good. Let's continue. If you're not tired yet, I would like to finish this today. Okay, a lens gives for a luminous object of 30 millimeters height, so G is 30 millimeters. Okay, located 40 centimeters from the optical center, so P is 40 centimeters. Okay, a real A prime B prime image of 45 millimeters, so G prime is 45 millimeters. What is the distance between the screen and the optical center of the lens? What is the focal length of the lens? Okay, let's do this one without the construction. You know how to do the construction. Let's solve this one theoretically. Okay. Question A is, what is the distance between the screen and the optical center of the lens? So the distance between the screen and the optical center of the lens is of course the distance between the image and the optical center, because the screen is where the image lives. Okay, so we are looking for P. Okay, and we know what? We know G, G prime, and we are looking for P prime. We know P, and we know P, G, and G prime. Okay, fine. What law are we going to use? Of course, we're going to use G prime over G is equal to P prime over P, the law of magnification. And this law tells us that P prime is equal to P times G prime over G. Okay, it's quite clear. Okay, so let's compute it. P is in centimeters. I'm going to put the units inside. Okay, P is in centimeters, so P prime is going to be in centimeters. And then G prime and G, we can transform into centimeters if we want, but since the units eliminate, we can also leave them in millimeters. It doesn't change anything. Okay, if you do what's G prime is 45 and G it's 30, if you put 45 over 30 or 4.5 over 3, is going to be the same. So this is 45 over 30, which is 1.5. 1.5 times 30, it's 60. Okay, so you have found a very nice precise value for P prime by computing it with the law of lenses, right? And then question B, what is the focal length of the lens? want to do that? Well, we have one law which says 1 over f is equal to 1 over p plus 1 over p prime. Okay, so now you can invert both sides of the law, and you can say that f is 1 over p plus 1 over p prime. Be careful with that. You cannot add up or do something different algebraically. It's like this. It's like this. Okay? And so now we compute that. It's 1 over, so we should now, if we want centimeters here, we should have centimeters down here. So p in centimeters is 40, and p prime, we just computed it, it's 60. So now if I compute all that, okay, 40 1 over x plus bracket 60 1 over x bracket equal, this gives me 0.041, but it's the inverse. I have to do 1 over x, and what I find is a very nice round number, which is 24 centimeters. Okay? So this is a typical example of solving an optics problem, a geometrical optics problem, based on the formulas rather than on the drawing. I leave it to you as an open exercise to do the drawing. You have all the data here. It's nothing complicated. Okay? Good. These are now the last two exercises. Try to do them. Try to do 17, and then we will do 18 and it will be over. Okay, let's continue. We now have to do exercise 17. A luminous object AB is located 80 centimeters from a screen. So we have P plus P prime, which is equal to 80 centimeters. Be careful about that. The object is located 80 centimeters from the screen. The distance from the object to the lens, which is P, you have to add to it the distance from the lens to the object, which is P prime, and the sum of the two is 80 centimeters. Okay? And the image A prime, B prime is the same size as the object, which in terms of lenses you can write as this, because G prime is the height of the image and G is the height of the object. Okay. What kind of lens should I use? Question A. What do you think? Of course, it's a convergent lens. Okay. Otherwise, you will never be able to have a real image that you can display on the screen. So we have a convergent lens. How far from the object should the lens be placed? Okay. How can we compute that? Well, we have G prime and G, we have P prime and P. Okay. So how can we play with that? Well, you know that G prime is equal to G. Okay, and now to answer question B, we can use the fact that G prime over G is P prime over P. G prime over G, since G prime is equal to G, has to be 1. Therefore, P prime over P has to be 1 too. Therefore, P prime has to be equal to P. So you can replace it in here. For instance, you replace P prime with P. You have 2P, which is equal to 80 centimeters. So P is equal to 40 centimeters. Okay. So the distance at which you should place the object before the lens is 40 centimeters. And what should be the focal length of the lens? Question C. You know that 1 over f is equal to 1 over p plus 1 over p prime. this implies that the focal length is 1 over p plus 1 over p prime, but p prime is equal to p, so we can say that this is 1 over 2 over p. 1 over p plus 1 over p is 2 over p, so it's p over 2, and p was 40 centimeters, so this is 20 centimeters. So here the answer is 20 centimeters. Okay? Now if you do your drawing, let's do it at a scale of 1 over 10. Okay, so we put the lens somewhere here in the middle. It's a convergent lens. We said that the focal distance is 20 centimeters, so here I will reduce it to 2 centimeters. Okay, these are f and f prime. The object is at p, which is equal to 40 centimeters. So the object is here and the image will be here, since p is equal to p prime. Okay, and then the height of the object, we don't know it, so let's take just 1 centimeter. Let's take a height of 1 centimeter. This result is not depending on the height, and here we should have an image of the same height. Of course it's going to be inverted, that image, so is this working? Is this correct? Here I drew the system with the pp prime, gg prime we have. Now let us check if I construct my principal rays. Let's check if this gives us indeed an image with the same size and which is inverted. Yes. Okay, of course this is giving you an image with the same size which is inverted and at a distance from the lens which is equal to the distance from the object. Okay, so here this is the object and here this is the image, and the screen you should put it here. Okay, now let's last exercise. Okay, it's a bit strange because we have meters and millimeters, and here you have something written which is the height of the image, which is 35 millimeters if I read properly. Okay, so what do we have? The distance from the tree to the lens, p is 120 meters. Then p prime, the distance from the lens to the screen, is 300 millimeters. I'm writing down everything like this, then we will choose one single unit. Then we have g, which we don't know, this is what we are trying to determine, and g prime, we know it, it's 35 millimeters. Okay, and question is what is the actual height of the tree? So for answering this question we need p prime over p is g prime over g, and what we are trying to determine is g, the height of the tree. Okay, this here is g, the height of the image here is g prime, this is p, this is p prime. Okay, so we use this relationship, we invert both sides, so g over g prime is p over p prime, and so g is equal to g primes times p over p prime. Okay, now I should have the same units for g and g prime and the same units for p and p prime, because these units here are going to cancel each other. So let's put everything in meters. Okay, so G prime in meters, it's 0.035 meters. Okay, it's 35 millimeters. P in meters, it's 120, and P prime in meters, it's 0.3. Right? So now if I compute that, it will take 1 second. If I compute that, I have 0.035 times 120 divided by 0.3, and this gives me 14 meters, which is a decent height for a tree. Okay, it's a high tree, but it's decent. It's a sequoia probably. Okay, that was question A. And question B, what is the focal length of the lens? Well, we have now we have PP prime, so again 1 over F is 1 over P plus 1 over P prime, gives us F is equal 1 over P plus 1 over P prime. And so I now have to compute the focal length. We want it in millimeters, right? So I will put everything in millimeters. It's going to be 1 over 120,000, 420 meters, plus 1 over 300 for P prime. Okay, and I compute that. 120,000 1 over x plus 300 1 over x equal 1 over x. This gives me 299.25 millimeters. So you see the tree is very far away. The rays arrive almost parallel to the optical axis, and so they are forming an image which is very close to the focal point. Okay, the smaller the image, the closer to the focal point it will form. And if you want, you can do the drawing of this situation. You have all the values. Okay, voila. So this concludes the exercises about optics. Next week we will either start with the sequel, or I will give you a formative evaluation. I don't know yet exactly. Okay, but please do these exercises and follow up. Finish these exercises so that this is behind us. Thank you. Bye bye. Have a nice day.